All right. Well, good morning, good afternoon, I should say. Today we're going to talk about Chapter 2. Last week we finished up by a power outage at the end of Chapter 1, so we were missing about the last 30 seconds of Chapter 1, so we won't really worry about that. So we'll just start again with Chapter 2. Now, Chapter 2 in this class is talking about the nature of potentials, and in fact, I've had a few questions already from students. So what do we mean by potentials when we talk about in electrochemistry? Well, that's what we're going to be discussing in Chapter 2. So if I can, let's see if we can get our video rotated appropriately. Okay. So we're going to be talking about potentials at interfaces, and we're going to actually go through Chapter 2 quite quickly. Not because it's not important, but I think a lot of that stuff can be benefited by self-study, and we'll outline the essentials of it, and you can read through it yourself. So we're going to be talking about potentials at interface and electrochemical potentials. First part of the chapter, we're going to discuss the thermodynamics of electrified interfaces, and that has to do with how the Nernst equation can be developed to develop a chemical and a cell potential. The first thing we have to consider when we talk about the thermodynamics of interfaces is to consider whether or not our interface is at equilibrium or not, because most of the standard thermodynamic treatments require that we have an equilibrium system. So let's discuss the idea of equilibrium first, especially as it pertains to electrochemical systems. In electrochemistry, and in fact many areas of chemistry, when we talk about equilibrium, we talk about reversible systems. And so we're going to discuss what we mean by reversible first. Let's get that door. The first idea is the fact that a system may or may not be chemically reversible, and this is a requirement for equilibrium to be true. And also we need to have a system that may be electrochemically reversible. But often we'll be happy and satisfied with a system that's practically reversible. And we'll discuss what we mean by those two things in a minute. In a practical sense, we're interested in systems that follow the Nernst equation. And remember, the Nernst equation can be formulated something like this, where we have a species O, which is an oxidized chemical species, undergoing some sort of an electron transfer to be reduced to species R. And if we put in some stoichiometric coefficients for that equation, we can write the Nernst equation as follows. The potential of that system, the electrochemical potential of that system is the standard potential of the system plus RT over NF, natural log of the activity of species O over the activity of species R. And of course, then we'll use our stoichiometric coefficients in that regard. And as I said, these are activities. Often, if we have a sufficiently dilute solution, we can substitute in concentrations without any worries about whether we're right or not. And this part, RT over F, R is the gas constant, T is the absolute temperature, and F is the Faraday. We've mentioned the Faraday before. And it has a value of 96,500 coulombs per per equivalent or per mole would be another way of saying it. So in a practical sense, if we have a system that gives us a cell potential that follows the Nernst equation, that gives us the proper potential according to the Nernst equation, we'll call that a practically reversible system. Now, we can see quickly that if we have a system such as this, where we have a reaction to form a species R that then undergoes a following chemical reaction at some rate to form, say, a species Z, that particular system probably is not going to be reversible, because as soon as we form R that can undergo a chemical reaction, that means that O and R really can't ever enter into an equilibrium system. And so we will not consider that to be at equilibrium. Now practically, that can be at equilibrium because this reaction, for example, may be quite slow. So if this reaction is on the order of hours or days or even years, we might still be able to suggest that O and R are in a practical practical equilibrium sense. So if we consider a system on the order of seconds for a follow-up chemical reaction that takes hours, we can still consider that to be a reversible system. Okay. Now once we consider a system to be in equilibrium, we can start to develop some thermodynamic ideas about that system. I think we mentioned last time that we can relate the free energy of our system, the change in free energy system, to the cell EMF, where the free energy of the system is equal to the minus n, the number of electrons transferred, F, where's Faraday again, and E is the cell potential, And we can correlate that also to the standard free energy of the reaction, to the standard cell potential. And this would refer to the situations when all substances are at unit activity or in standard states. So that would, for example, be a standard state would be the most standard, or the most stable form of material at a particular temperature and pressure. Now, as we discussed last time, there is a concept that we refer to as the EMF of a system. Actually, perhaps be better to call it with capital letters, EMF, or as you'll often see it with small letters as if it's a word. EMF, remember, stands for electromotive force, and that's the relationship between the physical concept of a cell potential and the requirement to relate the fact that our free energy has a assigned component to it. In other words, we have a free energy that can either be indicating a spontaneous reaction or a non-spontaneous reaction. Well, a cell potential does not have a sign associated with it naturally. We can assign a cell potential convention, but we don't have a cell potential that's assigned to it automatically. The EMF is a cell potential that has been assigned by convention a sign on it. And we can consider that when we write, for example, a reaction like this. Say zinc metal reacting with silver chloride to form zinc ions plus silver metal plus chloride ions. Now that overall cell reaction can be written as an actual cell like so. We have, say, a zinc electrode with zinc ions with unit activity, in a solution also with chloride ions, also with unit activity. with a silver chloride electrode. In other words, a silver wire with a silver chloride coating to it. And that particular cell can be written in this particular way. And as we outlined last time, we can calculate that cell potential. And if we calculate that cell potential, the EMF would be equal to plus 0.985 volts. All right. Now that kind of EMF would be measured by measuring the silver wire potential versus the zinc wire potential. In other words, if we had a multimeter, it has a negative lead and a positive lead, and we would hook that to the zinc wire, and the positive lead would be hooked to the silver wire, and that would be how we'd measure our EMF. So say we have a DMM, digital multimeter. Now if we switch that around so that we had the opposite direction of cell reaction, now our EMF would be equal to minus 0.985. Okay. So the EMF is proposing a direction of the reaction. Now in this case, though, all we've done is switch the direction of writing it. The cell potential stays the same, but the EMF has switched. Now notice also by our convention that the zinc electrode being on the left side is traditionally considered to be the anode. The anode because it's considered to be undergoing an oxidation as we've written it, and the silver wire would be considered to be the cathode on the right side. On this other way, we would be writing it so that the silver wire would be the anode undergoing oxidation, and the zinc electrode would be undergoing reduction. As you can see, because of the EMF is minus, that indicates a non-spontaneous direction for that reaction, and that's true. We wouldn't expect in this system the silver wire to be oxidized and the zinc to be reduced. It would be the opposite direction as we show up here. So given that idea of EMF, then we can go back to our idea of the free energy of the system. And you can see where we have to have a signed EMF to make our delta G the right sign. If we have a negative cell reaction, we have a delta G of a negative value. Again, that would be a non-spontaneous process. A positive delta G is a non-spontaneous process. A negative delta G is a spontaneous process. Now, I'm not going to go through the derivation, but we can also derive cell reactions relationships that relate the equilibrium constant to the cell potential, such as this. And I'll just leave that up there, and you can derive that yourself. And so, for example, the cell that we've just looked at up here, we can derive, for example, the solubility product of the silver chloride in solution as an equilibrium constant out of that particular cell, as long as we keep the other constants the same. All right. Well, as in every time we do this, we're going to consider the case that we're going to be measuring a cell potential as a function of at least two interfaces. We can't measure a single cell potential of any part of that cell. We have to measure, for example, the zinc with the zinc 2+ in concert with some other interface.